Hi, my name is Rishi Karir and I am going to present on the topic an Exergy study of vapor compression refrigeration system. So welcome to this presentation on the Exergy analysis of vapor compression refrigeration systems. In this presentation, we will explore how Exergy analysis can be used to design, improve and assess the performance of energy systems with a focus on the vapor compression refrigeration systems. We will discuss the methodology and the theory behind exergy analysis and how it can be used to determine a system's maximal performance and the locations of energy destructions. So here is the agenda, what we are going to discuss. We will start with the objective and we will do some literature review, and then we'll let you know about the system considerations and then some assumptions which we have made to do these calculations, and at the end of the presentation we will conclude it with the conclusion and the results. Here on the right side of the screen you can see the task accomplished by both of us, and we have segregated our project and the tasks, so it's defined here. So this slide speaks about the objective of our project work. The most popular method for thermal system analysis is first law of thermodynamics, which emphasizes energy conservation without revealing where or how much system's performance is being sacrificed. So here are like three main goals of this project work. The first is to carry out a review of the literature and find related studies. Second is to investigate exergy loss. Third is to determine COP, that is coefficient of performance. In total, 10 number of papers are reviewed. 80% of papers are from the year 2015 to 2021. System consideration. Here consider system is the refrigeration system as depicted on the screen, which is a vital component in many cooling systems. The refrigeration cycle consists of four major components: the compressor, condenser, throttling valve, and evaporator. In this particular refrigeration system, the refrigerant enters the compressor in state 1 and is compressed in the process 1 to 2. It exits the compressor as a superheated vapor and moves to condenser. In the state 3, the refrigerant becomes a subcooled liquid and is further throttled in the process 3 to 4. The cycle is closed by vaporization process 4 to 1 in the evaporator. Listed are some assumptions which we have made for our calculations.
Now we will look at a ideal vapor compression refrigeration cycle that uses R134A refrigerant. Here, the refrigerant absorbs the heat from a space at 5 degrees Celsius and rejects it to 25 degrees Celsius. As it evaporates at minus 10 degrees Celsius and condenses at 57.9 degrees Celsius. Now, as we seen, the lower temperature is 5 degrees Celsius and higher temperature is 25 degrees Celsius. Since we are studying a refrigerator cycle, the dead state temperature is equal to TH, that is 25 degrees Celsius. Now from table A11 to A13, we can calculate the entropy and enthalpy of four states. As we can see from the figure, the temperature at minus 10 degrees Celsius, we have enthalpy of 244.55 kilojoule per kilogram and entropy of 0.9378 kilojoule per kilogram Kelvin. Now in state 2, at minus 10 degrees Celsius, we have saturated pressure of 1600 kilopascal. Now to find enthalpy at state 2, we have to do interpolation method. By doing that, we can get the enthalpy at state 2 of 287.89 kilojoule per kilogram. Now at state 3, at a pressure of 1600 kilopascal, we can get the entropy and enthalpy from the given table. As we know, the enthalpy at state 3 and state 4 will be the same. Now at state 4, to find the entropy at state 4, we have to first calculate the quality of steam. We can find the quality of steam from the given equation. After calculating, we can get the entropy at state 4 of 0.5252 kJ per kilogram Kelvin. Now that we have enthalpy at all the states, we can find the heat removed from the refrigerated space, heat rejected to the environment, and net work done to the compressor. Now we can calculate the coefficient of performance of the cycle from QL and Win, which will be 2.506. Now we will calculate the Exergy destruction at each component. In compressor, as we know, the entropy at S2 and S1 is same, so the entropy generation will be 0 and the Exergy destruction will be 0 too. In condenser, we can find the entropy generation from the given equation. After that, we can calculate the Exergy destruction from T0 into S generation, which will be 15.27 kJ per kilogram. Now, in the same way, we can calculate the entropy generation at expansion valve from S4 and S3, and after that we can calculate the Exergy destruction of expansion valve, which will be 13.69 kJ per kilogram. In the same way, we can calculate the Exergy destruction at evaporator, which will be 6.56 kJ per kilogram. The total Exergy destruction of the cycle will be the summation of Exergy destruction of all four parts, which will be 35.52 kJ per kilogram. Now we can calculate the Exergy destruction of heat transferred from low temperature medium, which will be 7.813 kJ per kilogram. Now the second law efficiency can be calculated from the given formula, which will be 18%. For the second law efficiency of compressor can be calculated from the given formula. As we know, the entropy of state 2 and state 1 is same, so the efficiency of compressor will be 100%. In the same way, we can calculate the second law efficiency of evaporator from the given equations, which will be 54.4%. As we seen, we can get the coefficient of performance of 2.506, which indicates high efficiency of the cycle. Since it was an ideal case, there is no Exergy destruction in compressor. However, we can see the irreversibility in condenser, expansion valve and evaporator. In the last, the second law efficiency is 18%, which shows the effective cooling operation. In conclusion, as we discussed earlier, the results were based on an ideal case. However, in real-world applications, we can see the irreversibility in compressor and also Exergy destruction due to friction losses. That's why more studies required to determine how this irreversibility affect the refrigeration cycle's overall efficiency. Finally, this study provides useful insights to the performance of refrigerant R134A to the system and also Exergy analysis of different parts and the whole system. These are the references that we used in our study.